Okay, so the last section you should have watched was 5.2, and I'm moving on to 5.4 now on purpose. We'll come back to 5.3 once we cover 5.4. My own preference is to cover the general multiplication rule first, which is the topic of discussion in 5.4. And then once we've done that, we can come back to 5.3, which talks about the multiplication rule for independent events. It just makes more sense to me to start with the general and then go to the specific later than it does to start with the specific and then move out to the general. So anyway, so in 5.2 we talked about probability of E or F. In 5.3 and 5.4 we're going to be talking about probability of E and F. Okay. This is the same probability of E and F that showed up in the general addition rule when we were talking about probability of E or F in 5.2, right? So we're just going to talk about that idea in a little bit more detail. Okay. In order to do so, we first need to understand a little bit about conditional probability. So conditional probability is hugely important. Later on in the semester, when we're performing inference, a lot of that inference is going to be based on conditional probabilities. Okay. So the notation for conditional probability is this notation here. You have two events with a vertical line between them. We read this symbol, probability of E given F. So this line is read given. Right, so our probability of E given F. It's the probability that E occurs if we assume that F definitely occurs. It's like, so if you know for a fact that F occurs, what's the probability that E will occur? Whatever you do, do not think of this as the probability of E over F, okay? That's not what that vertical line means. It's not a fraction bar. So it's not like probability of E divided by probability of F or probability of E over F, whatever that would mean, right? This is completely this is total nonsense. And this is not what that means, right? So there's not equality between this and that, okay? Probability of E given F, like I said, is the probability E occurs if you know that F has occurred. It's not the same concept of probability of E and F, and this is sometimes confusing for students because you might kind of think, well, you're assuming that F occurs and then you're computing probability of E occurs. That means that both E and F occurred. So aren't these two things the same? But the answer is no. Probability of E and F is the probability that E and F both occur, but without any assumption or any prior knowledge that either of these things actually do occur. Whereas probability of E given F, you know for a fact that F occurs going into the probability. And so they are different, and I'll give you some examples to demonstrate the difference between them. So this first example says, suppose that you roll a fair six-sided die. Let E be the event that the number rolled is greater than or equal to 4, and let F be the event that the number rolled is even. It might be useful to write these out. So E is greater than or equal to 4. So that would be 4, 5, or 6. F is even. So that would be 2, 4, or 6. Since we're talking about a six-sided die, right? Okay, so probability of E, that would be 3 out of 6, right? Probability of F is also going to be 3 out of 6. Probability of E and F. Probability of E and F. Well, what do they have in common? They both have, they have 4s in common, they have 6s in common. So I think there are two ways that E and F could occur. And that is if you roll a 4 or you roll a 6, right? If you roll a 4, then E and F are both satisfied. If you roll a 6, then E and F are both satisfied. If you roll a 5, then E is satisfied, but F is not. And so E and F is not satisfied, right? But there are two ways that you could satisfy both of those events at the same time. and that's by rolling a 4 or by rolling a 6. So probability of E and F is 2 out of 6. In other words, 1/3. Now part D, the new thing. What is probability of E given F? So this vertical line, this given F business, that means that we know for a fact that F occurs. We know for a fact that F occurs. So it's like the rest of the outcomes don't even exist, right? It's like we know that this, we're either going to roll a 2, 4, or 6. And so knowing that, now what's the probability that E occurs? Well, if you happen to roll a 2, then E does not occur. But if you roll a 4 or a 6, then E does occur, right? So there are 2 ways that E can occur if you know that F has occurred, right? So probability of E given F, 2 ways that E can occur. But notice that there are only 3 possibilities because you know for a fact that F occurs. So there aren't 6 possible outcomes anymore. 1, 3, and 5 are out of the question. Okay, because you know that F has to occur. So there are only 3 possibilities now. So probability of E given F is 2 out of 3. So, and now you can see the difference, right? It's like with probability of E and F, you had 6 possibilities. And there were 2 ways that they could both happen. With probability of E given F, you only have 3 possibilities because you know that F occurs, right? So you only have 3 possibilities, and then there are 2 ways that they can both happen. So the difference between probability of E and F and probability of E given F is the denominator, right? The numerator is going to be the same, and that's where you get confused when you're like, wait, aren't these two concepts the same thing? It's like what you're thinking of is the numerator, and you're right. The numerators are going to be the same, but the denominators are going to be different. Okay. Sort of one way to think about probability of E given F is that this given F is a restriction. You're not looking at the entire sample space anymore. You're only looking at event F. So it changes your denominator, right? You only have 3 possibilities instead of 6. Let's do another set of examples. This one says the following data represent the number of communication activities used by a random sample of teenagers in a given week. So there are some male and female teenagers in the study, and then some of them did no communication activities. And by communication activities, I think they mean like texting, calling, social media, whatever, right? So there were some individuals that didn't do any of those activities. Maybe they were camping or something, so their cell phones didn't work. And then there were some individuals that did 3 different kinds of communication activities, right? And then, of course, there were individuals in the middle. Now it says, an individual from this study is chosen at random. Let A be the event that the individual is male. Let B be the event that the individual does 3 activities. So first we're asked to compute probability of A. So what's the probability that the individual chosen is male? Well, in this particular survey, there were 200 males in total out of 400 individuals. Okay, so that's 1/2. Part B says, compute probability of A given B. Ooh. Probability of A given B. So probability that they're male, given that they did 3 activities. So what's the probability that they're male, given that they did 3 activities? So given that they did 3 activities, that means that we're restricting ourselves to this column. We're not looking at the entire sample space anymore. We're only looking at the people who did 3 activities. And given that they did 3 activities now, what's the probability that they're male? And that would be 40 out of 111, right? There were 40 males who did 3 activities out of 111 individuals in total who did 3 activities. So it would be, so probability of A given B is 40 out of 111. Which is about 0.360. This is 0.5. Okay, so that's interesting. You'll notice that the probability that they were male is 50%, but the probability that they're male given that they did 3 activities, 36%. So obviously the communication activities that you do, the number of communication activities that you do, is sort of dependent in some sense on your gender, right? Okay, part C says compute probability of B given A. You might be thinking, wait, how is this not the same as that? But they are totally different concepts, right? So it's not like addition where you can do it in any order you want, right? The order matters here. So here we're looking for probability that the person does 3 activities given that they're male, right? 3 activities given that they're male. So this time we're restricting our attention to the males in the study, right? We're restricting our attention to this row, men in the study. And now we want to know, well, if the chosen individual is a male, now what's the probability they did 3 activities? And that would be 40 out of 200. Okay, so 40 out of 200. So you can see that these two things are not the same. Again, the numerators are the same because the numerators have to be where the 2 events overlap, right? They have to be 40, but the denominators are different. Because here we were restricting our attention to 3 activities, right? So the denominator was 111. And here we were restricting our attention to males, so the denominator was 200. 40 out of 200. Okay, in part D, compute probability of A and B. Uh-oh, train's coming. I'm going to mute as soon as they start honking their horn. Probability of A and B. Well, there were 40 individuals in this study who were both male and did 3 activities, out of 400 individuals in total. Okay, you may be able to hear the train still passing by. So I live in this crazy situation where there's a railroad track that goes right behind my backyard. And the train comes maybe 5 times a week. So it doesn't come like every day. And it usually doesn't come more than once a day if it does come by. But anyway, it's just kind of, it doesn't come by often enough for it to be super annoying. Unless I'm in the middle of recording a lecture like I am right now. But in fact, it's kind of fun when they come by. My kids like to, wave at them, and then the train conductor will, honk the horn and stuff. Anyway, but finishing this problem, right? This is going to be 10%. Okay, but again, you can see what's changing here in parts B, C, and D are the denominators, right? The denominators. Here in part D, we weren't restricting our attention to anything. We were looking at the entire sample space. Here we were restricting our attention to the men in the study, and here we were restricting our attention to the people who had done 3 activities. Okay, and you get different answers in all 3 situations. One thing that you'll notice right away that we pointed out is that this operator, this sort of conditional thing, this given is not commutative, right? So probability of E given F is not the same thing as the probability of F given E. Okay? And then another thing that it illustrates, as I've been saying, is that what probability E given F does is restrict our attention to only F. Okay? So probability of E is the probability that out of all of the events in the sample space, E is what occurs. Probability of E given F is the probability that out of all of the events in F, E is what occurs. Okay, so that's what conditional probability means. Oh goodness, all right, so here's another example. It says a survey was conducted by the Gallup organization conducted May 8th through 11th, 2008, in which 1,017 adult Americans were asked, which of the following statements comes closest to your belief about God? You believe in God, you don't believe in God, but you do believe in a universal spirit or higher power, or you don't believe in either. The results of the survey by region of country are given in the table below. So here we have the region of country, right? East, Midwest, South, and West. And then we have their response, right? Believe in God, believe in universal spirit, don't believe in either. So there were 9 individuals in the South who said that they didn't believe in either, right? There were 167 people in total who said that they believed in some kind of universal spirit. And there were 254 people in total who were surveyed from the Midwest, right? So, and again, 1,017 was the grand total number of people in this survey. So what I want you to do is pause the video, see if you can answer these questions, okay? So part A says, what's the probability that a randomly selected adult American believes in God and lives in the East? So I'll let you pause the video and see if you can do that one. Okay, here's my solution. Probability they believe in God and live in the East. That means they have to be in this column and they have to be in this row. So there's 204 of those individuals, right? 204 individuals who believe in God and live in the East. So it's 204, and we're not restricting our attention to anything. So it's 204 out of 1,017. I'm not going to change it into a decimal. I don't really care at this point. Part B says, what's the probability that a randomly selected adult American who lives in the East believes in God? So what's the probability that someone who lives in the East believes in God? I'll let you pause the video, see if you can work that out. Here's my solution. Okay, so we want the probability that someone who lives in the East believes in God. So we want them to believe in God, right? We want the probability that the person believes in God, and what we're given, what we know, is that they live in the East, right? So the probability that they believe in God, given that they live in the East, right? That's really how we would translate this question, right? Probability they believe in God, given that they live in the East. Well, so then we're going to restrict our attention to people who live in the East, right? So we're restricting our attention to this top row. And now we're looking for the people who believe in God. There are 204 of those, right? So 204 out of 1,017. And then finally part C. Or, oh, I'm sorry. I led you astray. 204, not out of 1017, out of 255, right? Ooh, out of 255. Because we're restricting our attention just to the top row. Yeah, my apologies. Yeah, it should be 204 out of 255. Okay, and then part C. What's the probability that a randomly selected adult American who believes in God lives in the East? So give the video a pause, see if you can work that one out. Okay, this time the restriction goes in the other direction. We want the person to live in the East, and what we're told about them is that they believe in God. Right? We're told that they believe in God. Now, what's the probability that they live in the East? So we want probability they live in the East, given that they believe in God. So we're restricting our attention to this column right here. So probability that they live in the East, given that they believe in God, 204 out of 787. Okay. So that's the idea. Hopefully you're catching on to that idea here. So now we've taken this detour talking about conditional probabilities when what we set out to discuss was and probabilities. What we really wanted to know was, what is the probability of E and F? What's a good formula for that? Well, here it is in all of its glory. And you can see that in order to write down this formula, we had to know about conditional probabilities. But the probability that two events, E and F, both occur is probability of E times probability of F given E. Just to kind of convince you of this, if you refer back to example 2, so if you refer back to example 2, we're claiming that probability of A and B should be the same thing as probability of A times probability of B given A. Well, we can verify that, right? Probability of A, we said was 0.5. Probability B given A, we said was 0.2. And 0.5 times 0.2 is 0.10, 0.1, right? Sure enough, right? We get the same answer. So, so yeah, this is the formula for probability of A and B. A common misconception is that probability of A and B is just probability of A times probability of B. That's true sometimes. That'll be the topic of discussion in 5.3. Okay, so that is true sometimes, but generally speaking, that is not the case. Generally speaking, probability of A and B is probability of A times probability of B given A, right? Another thing to consider is, so we have another formula that we could use in place of this one, because probability of E and F is the same thing as probability of F and E, right? Both of these probabilities are the probability that E and F both occur out of the entire sample space. So you're going to get the same answer if you compute probability of E and F as you would get if you computed probability of F and E. So if you think about what probability of F and E would be, so think about this formula here, and instead of thinking of the letters, think of it like the first thing and the second thing, right? So we have probability of first and second is probability of first times probability of second given first. So if we rearrange the letters, so now F is the first and E is the second, probability of F and E is going to be probability of the first times the probability of the second given the first. So probability of F and E is probability of F times probability of E given F. But since probability of E and F and probability of F and E are the same, that must mean that this formula here and this formula here are equivalent. So we actually have two different ways to think about probability of E and F. We can either use this formula, right? Probability of E and F is probability of E times probability of F given E, or we can use this formula, right? Probability of E and F is probability of F times probability of E given F. This is good news for us because it gives us actually two ways it gives us more tools to work with if we're trying to solve a problem. And the more tools you have, the better, right? The more problems you can solve. So let me give you an example of these formulas in action. Now, just like we said when we looked at probability of E or F, right, back in 5.2, we said you don't actually need the formulas. A lot of times you can just figure it out just by looking at the charts and stuff, and that's certainly true, right? Like in all of the previous examples we saw, like for example in part A on number 3, we computed an AND probability without having to rely on a formula to do it, right? So we didn't need a formula for this particular problem. But in some scenarios, we do have to rely on formulas. For example, this one says the probability that a speeding driver gets pulled over is 0.8. The probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. I believe that. I think if you're pulled over, there's a 90% chance you get a ticket. That makes sense to me. But an 80% chance that you get pulled over if you're speeding, that's not true. That's definitely not true. People speed all the time, but they usually don't get pulled over for it. So, so that's like maybe in the CHP's wildest dreams, 80% of speeders would get pulled over. But in reality, that number is probably a lot lower. But anyway, we'll just go with it. We'll just assume that this is true. So if you're speeding, there's an 80% chance you get pulled over. And if you get pulled over, there's a 90% chance you're going to get a ticket. Now, what's the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? Okay. Now, we just got done talking about a multiplication rule. And here we have two numbers to work with. So your instinct is probably to just multiply those two numbers together and hope for the best. And in this case, that's going to work out for you pretty well because you're going to get the correct answer. However, not all problems are that easy. So it's a good idea for you to actually think through what you're doing. And my advice would be to rewrite the information that you're given using correct probability notation. This will help you to apply the correct formula, all right? So in this case, here's how I would do that. I would say probability speeding driver gets pulled over is 0.8. So I'm gonna say probability someone gets pulled over is 0.8. Then it says the probability the driver gets a ticket, given that he or she pulled over, is 0.9. So the probability that they get a ticket, given that they were pulled over, is 0.9. And now we're being asked to compute the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket. So we want the probability that they get pulled over and that they get a ticket. So applying our multiplication rule that we just talked about on the previous page, we would say, well, this is the probability that they get pulled over times the probability that they get a ticket, given that they're pulled over. And those just so happen to be the pieces of information that we were given in the problem, right? So this would be 0.8 times 0.9, which is 0.72. Okay. So that's good. That's all well and good, right? And so you could say, well, it's just too much work to have to write all this stuff down, right? It's really not. And at least if you write all this stuff down, you can be totally and 100% confident that your answer is correct, okay? So you're not guessing at all. You know that this is the correct answer, okay? So let's do another one. This one's a little more challenging. Okay, so this one says, according to a Harris poll, 60% of adult Americans have tattoos, 50% have pierced ears, and 65% of people with pierced ears have tattoos. What is the probability that a randomly selected adult American has one or more tattoos and pierced ears? Okay. Now, as you can see, this problem is a lot more challenging than the previous one because you're given three pieces of information. You're given three numbers, and you're not going to use all of them. You're only going to use two of them. If you think about the multiplication rule, you're only going to be using two numbers. And so the question is, which two do I use? Do I do 0.6 times 0.5, or do I do 0.6 times 0.65, or do I do 0.5 times 0.65? And I can tell you right now that something that students have a tendency to do is that they just guess and check, right? They say, well, I'm just going to do 0.6 times 0.5 and see what I get, and then I'll check the back of the book. And if it's the wrong answer, well, then I'll come back and I'll try 0.6 times 0.65, and then I'll check to see if that's right. And if it's wrong, I'll come back and I'll do 0.5, right? And they do this until they get the correct answer. The trouble with that is, you know, you circle the answer and you're so happy that you got the correct answer, but you got the answer and you finished the problem, but you don't understand the problem. Going through the homework like that is not helpful. You might as well not do the homework if that's the approach that you're going to take. because it's not going to help you to do well on the test, right? What you need to do is spend the amount of time really familiarizing yourself with the problem, really truly understanding the problem before you jump to try to, guess at a solution. Really try to understand what's going on, and then you can be confident that your answer is correct. That's the kind of studying that's going to be useful for you on tests and quizzes. That's how you're going to learn the information, right? So let's do that. Let's put forward, or let's put forth the effort that we need to put forth in order to actually understand what's going on here. So it says 60% of adult Americans have tattoos. I'm going to call that P of T, right? Probability they have a tattoo, 60%. Then it says 50% have pierced ears. So I'm going to call that P of E, right? 50% have pierced ears. So probability you have tattoos, 60%. Probability you have pierced ears, 50%. And now the last statement says 65% of people with pierced ears have tattoos. Now let's be very careful about how we write this down. 65% of people with pierced ears have tattoos. So what we know about these individuals is that they have pierced ears, right? So we're given that they have pierced ears. And then we're told if they have pierced ears, then the probability they have a tattoo is 65%. So those are the pieces of information we're given. We're given probability of T, probability of E, and probability of T given E. Now what are we asked for? We're asked for what's the probability that a randomly selected adult American has one or more tattoos and pierced ears, right? So we're looking for the probability to have tattoos and pierced ears. Okay, so probability they have tattoos and pierced ears. This is going to be probability they have tattoos times probability they have pierced ears, given that they have tattoos. But we have a problem here, right? Because we're given this piece of information, we know that it's 0.6. But we're not given this piece of information. We don't know what the probability of E given T is. We were given this probability, right? Probability of T given E. So we don't have enough information to use this formula. Fortunately, as we said on the previous page, there's another formula we can use. Probability of T and E is the same thing as probability of E and T. So if I change my perspective a little bit, this is going to be probability of E times probability of T given E. Okay, and I have both of those pieces of information, right? Like I know probability of E is 0.5, and I know probability of T given E is 0.65. Okay, 0.5 times 0.65 is 0.325. Okay, and there we go. And at this point, I'm totally 100% confident that this is the correct answer because I spent the time that I needed to spend in order to understand the problem. Okay, so 0.325. So that's my advice on the homework, right? Do that. If you're confronted with a problem like this, translate it into correct probability notation, and then that'll make answering the question a lot easier. Okay, so there's your homework assignment. We'll see you back in 5.3.